All right, so good afternoon, everyone. So we're back to our live stream for the question and answers. So today we're going to check several answers, pretty common question, and then we will verify the answer, and also we can go through the answer together. So without further ado, let's get started. Okay, so for today we're looking at first year chemistry. We are going to look at first year chemistry, the common questions. We go through roughly around maybe 10 to 12, maybe 15 questions today, and then we will look at the answer together and to verify the solution. Okay, first of all, um, let's look at our first question. Okay, so the first question is enter the molar molecular formula for butane C4H10 and express that in chemical formula. Okay, so first of all, we have to find out the actually, I think for this question it sounds a little bit weird. The reason is that we are going to enter the molecular formula. I'm sorry, I just have an alarm going on. Okay, I'm very sorry because there's just a fire alarm happened in my condo, so I hope everything is fine. Okay, so give me a second. Okay, so let's get back to our question. So we have a molecule of. So first of all, the question sounds kind of weird. The reason is that we have to enter the molecular formula, but we have to express that in a chemical formula. So actually, chemical formula contain. Imagine a chemical formula is just telling you, or asking, telling what kind of formula, what kind of method we're going to describe chemical. So for we can have molecular formula, we can have a condensed formula, we can have empirical formula. So I believe this question just want to ask you to enter the molecular formula for butane, and then we are going to just want to tell you that molecular formula also is part of the chemical formula. So from here, I would say that the question, I would say it's kind of it's confusing, but okay, when we're looking at butane, butane is a four carbon hydrocarbon. So we have four carbon. So let me look at our So we have well, I'm going to draw the whole molecule right here. So we have C4, and also we fill all of the bonding with hydrogen. So we will have C4H4. I'm very a little bit further away from the screen, but we draw again. So for butane, we know that we have all four carbons, and then for each four carbon, we are going to connect that with the hydrogen in order to fulfill the octet rule, and at the same time, they all have a hydrogen because a hydrocarbon. So from here, we know that we have four carbon, and also if you actually count that, we have 10 hydrogen. Okay, so yes, I would say that the answer is correct. The molecular formula is C4H10, and also this will be you can solve the Lewis structure as well. And then I think that for this question, the question is kind of confusing. So I believe it is asked for molecular formula instead molecular formula. Not all of the chemical formula. All right, so let's get moving. Okay, so this is correct. Okay, so move on to the second question. So for the second question, we have an equilibrium of a mixture of a PCl5, PCl3, and also Cl2. And all of it, they have partial pressure of 217 torr, 13.2 torr, 13.2 torr respectively. And then another excess chlorine gas is going to inject in the mixture. And the total pressure just before everything to re-establish the equilibrium, it will be 263 torr. So, and then we allow the system to equilibrate. So, and the appropriate chemical reactions is PCl3 plus Cl2 to PCl5. So I'm going to copy and paste that. So we have PCl3. Yeah, there's something wrong with that. All right, so we have PCl3 with gas. We're going to mix with chlorine gas, and then going to form PCl5. All right, so I'm going to put a gas over here. Okay, so we're going to calculate the new partial pressure after equilibrium we established. All right, so maybe I move it a little bit so we have a little more space on the on my on screen on the right. Okay, so let's go through the answers part by part. Okay, so yeah, we already have a equation given over here, and I forgot that is equilibrium. So I should have a double arrow. So initially, we can calculate the Kp, and we are going to take the initial initial pressure, plug in the Kp expression. All right, so I would like to just write out the Kp expression. So we know that the Kp expression will be equals to the partial pressure of our product over the partial pressure of our reactant multiplied together. So this will be the expression of our the equilibrium constant in pressure. All right, so yeah, we just plugged in a number. It's not that difficult. It's 1.2454. Yeah, and this is right. Yeah, this is definitely right. Okay, so after adding the chlorine gas, we know that it will be PCl5 will be 217, and then PCl3 will be 13.2, and then chlorine will be 13.2 plus X. Okay, so we know that the partial pressure will be, actually the total pressure after adding chlorine will be 263. So yeah, so we are going to add everything together, and also we just don't know how much is going to of chlorine gas is going to add. So that's why we let it at X. So from here, we add everything together, including the excess chlorine gas, and then we are 263. So from here, you can solve for the equation, and we should be find that the total pressure will be 19.6 torr. It's being added to the equation. Sorry, the reaction. Okay, so from here, it's just kind of confusing, I think, from the solution over here. So maybe we just go step by step. Okay, so when we go back to our reaction equation over here, we have an equilibrium. So for equilibrium, we can look at a Letellier principle. So we have PCl3, we have chlorine, and then we have PCl5. Okay, so from here, imagine we increase the amount, the pressure of chlorine gas. So what will happen to the equilibrium? So we increase the amount of reactant, and the equilibrium, we want to re-establish a new equilibrium position by removing the excess chlorine gas. So the whole equilibrium will shift to the right. All right, so if we are going to write our ice table, so I am going to go down a little bit. So we want to write our ice table. Okay, so first of all, we have 217 PCl5, but we add in more. We add in more chlorine gas. So we are expecting the PCl5 going to increase, but the Cl2 and PCl3 are going to decrease. So therefore, we are going to set the ice table. When we set the ice table, the initial condition will be the one just after adding the chlorine gas. Okay, so from here, we know that the chlorine, the PCl3 will be 13.2 torr. And then for the chlorine gas, we will have 13. Let me look at that. 13, yeah, say 13.2 plus 19.6. If you see that on the left, we already have 19.6 of chlorine being added. Okay, so if you do the math, you should be able to find that it will be 32.8. 32.8. So I'm going to change it to 32.8. Okay, so again, by Letellier principle, we know that the reagent we are going to decrease in order to remove the excess chlorine, and then we're going to have more of our PCl5. So at the end of the day, we are going to establish this equilibrium concentration. Okay, so the next step we will just plug in everything here back to our equilibrium constant expression. Okay, so we are going to back to our the solution on the left. That's exactly what is going on. So we are going to plug in the expression, and then we are going to solve for that. It takes some time, but it's a very simple algebra. We are going to solve for that as a quadratic equation, and you should be able to find that the x will be equals to either 6.4 or 40.4. Oh, but for this case, we're going to ignore 14.4. The reason is that x cannot be bigger than 30.2. If so, then we don't have any PCL3 left. And for this case, it is not reasonable. It should not be happen. So that's why we're going to choose 6.4 as our answers. And then we just plug in 6.4 as x, and then we can find out the PCL5 will be 217. PCL3 will be 6.8, CL2 will be 26.4. Okay, so for my comment for this question and solution is that the solution is correct. However, the solution is kind of confusing. Especially, you can see that because the solution didn't show using an ice table. If an ice table is used to find out the equilibrium concentration, actually it's equilibrium pressure. This would be more easier to explain. Okay, so this will be the second question on equilibrium. So this is correct, so we can keep going on. So let me add one more section so I can have more space. All right. Okay, so for question number 3, we have to find the molar mass of iron. Okay, so first of all, for this, let's look at the answers. The molar mass of iron is measured as gram per mole, and it's equals to 55.845 gram per mole. Molar mass, of course, is the mass per number of mole of element or per number of mole of substance. So from here, we are looking for the molar mass of iron. So we are going to you can use Google, or you can look at your textbook from the periodic table. You can find the corresponding molar mass for iron or for different element. Okay, so but sometimes your periodic table will show that the atomic mass. But actually, the conversion factor between the atomic mass and also the atomic mass unit will be equals to AMU, or A.M.U. 1 AMU, essentially, the conversion factor is equal to 1 gram per mole. Okay, keep in mind that AMU and gram per mole, they are different. It's just the conversion factor. They have the same number, so it's 1-to-1 ratio. Okay, so for this case, the solution is correct. Okay, so let's look at the second paragraph. The very first table, the standardized atomic weight is called the atomic mass, because at first we don't use gram per mole, we use atomic mass, and introduced by John Dalton in 1805. We have a system to relative atomic mass of hydrogen to be 1 and carbon to be 12, and then to the relative mass. And then later we are going to, because we are much more concerned in the amount of reagent that we use to install chemistry, so it's not that convenient to use atomic mass unit, so that's why we switch to use gram per mole. And for mole is that for AMU, we are looking at one single atom. For molar mass, we are looking at the mass for 1 mole. And for 1 mole of substance will be equal to 6.02 times 10 to the power 23. So for example, for one atom, we have one iron atom. It will be equals to 55.845 AMU. And then for 1 mole of iron, it will be equals to 55.845 gram per mole. So that because we are looking at different units, although the number is different, but we are looking at different number of elements or molecule. So the answers are correct, and also the explanation is detailed. Okay, so let's keep going. All right, so we are looking at another question. So we're looking at colligative properties. Okay, so first of all, which of the following aqueous solution you expect to have lowest freezing point? So we are looking at freezing point depression. So when we create a solution, so the freezing point, I will just call it FP, is going to decrease. It's one of the properties of a solution. Okay, so we have 0.4 molality. It's not molarity, so small letter m, so molality, potassium sulfate. We have 0.4 sodium chloride, and we have 0.4 glucose, and also we have 0.04 potassium sulfate, and also 0.04 sodium chloride. Okay, so let's have a look on our the provided solution. Okay, so the freezing point of water is depressed by addition of the solute. Yeah, this is the for me the one of the consequence or one of the properties that when we have a solvent, with a solute dissolved to become solution, so the freezing point will decrease. And the amount of the depression in the freezing point depends on the molality of the solute particle in that solution. Higher the molarity, lower the freezing point. Okay, so I just dropping down a very important point here, is that we have a higher molality of the solute, then the freezing point will be further decreased with a larger degree. Okay, so we are going to find out the actual amount of solutes in our solution. So first of all, for A, we have 0.4 molar K2SO4. So for each individual ion, so for potassium, because it's K2SO4, so let me write on the right. So we have K2SO4. Assume that we have 0.4 molality of that. If you're only looking at a potassium ion, so for each ionic, you can say for each ionic compound, each K2SO4, it will have 2 potassium. So therefore, the potassium will be equal to 0.4 times 2, 0.8 molar, and then for sulfate ion will be equal to 0.4. So this is exactly what the calculation is going on over here. And the total amount of particle or ion will be equal to 0.8 plus 0.4, 1.2. We're going to carry out the same calculation for B, C, D, and E. Okay, so for B, we have 0.4 sodium chloride, so we have 0.4 sodium, 0.4 chloride. The total number of molality of iron will be 0.8. And then for glucose, we have 0.4, but we only have 0.4. All right, so I will go in details later, but let's go through the solution together to see if any calculation error. So we have 0.04 potassium sulfate, we have 0.08 potassium, and 0.04, so we have 0.12 molality. And then we have 0.04 sodium chloride, 0.04 sodium, and 0.04 chloride ion, and then the total will be 0.08 molality. So from here, the correlation is correct. Okay, so however, when we're looking at C, we are looking at C. So we're looking at something called glucose. So glucose is an organic compound, is an organic molecule. Pretty much is a sugar. So for this glucose, so assume we have this glucose is water soluble. We are going to dissolve that in water. So create a solution. So we have C2H12O6, and then we have an aqueous solution. Okay, so for glucose molecule, what it's going to do when dissolve water is that first of all, we have a glucose solid is a crystal. So this crystal is contain different glucose molecules. So they just stack together to form a crystal. But when they dissolve in water, they go individual glucose molecule going to surrounded by water. So they form a hydration shell. So they're going to be dissolved. When they dissolve in water, they still exist. as a whole glucose molecule. It's still one intact glucose molecule. Okay, so therefore, when we have 0.4 molality, or say small capital M of glucose, when we start, and then when after dissolved, the total amount of particle or total amount of molecule is still equals to 0.4 molality, because it doesn't do any dissociation. Okay, when we go back to look at our ionic compound, why we have to separate two ions together and then we multiply them and then we add them together. The reason is that when we have our ionic compound going into water, it's going to be dissociate to become potassium. So I'll go right here, potassium, and also sulfate ion. So the whole solid is going to be dissociate, ionize, separate in two different components. So that's why when we are going to look at ionic compound in this substance solution, we have to take in consideration the actual molarity of the particle will increase due to this dissociation. Okay, so we already calculate the actual number or concentration of different solution, the particle in different solution. The next step is we are going to find out which one had the highest, and this should give the highest amount of freezing point dispersion. So if you actually look for the freezing point dispersion, the equation, delta F equals to constant. This constant, I forgot the name, but I would call it the freezing point dispersion constant. It depends on the solvent. And then we are going to take a negative with the molarity of our total particle. Sometimes you will see an I over there. This is called the Wang Hoff factor to account any dissociation in the molecule. For instance, for this case, when we have a 0.4 over here, and then we know that this ionic compound is going to dissociate in three different components. We have 2 potassium and 1 sulfate. So that's why we have to add a Wang Hoff factor times 3 in order to find out the actual amount of actual concentration of the particle in the solution. So that's why sometimes you consider a Wang Hoff factor. But if you know that for the molarity over here, you just plug in the total concentration, then you'll be fine. So from here, you can see that the change in the freezing point is directionally proportional to the concentration. So if you have a higher concentration, we have a higher dispersion. So again, obviously, this A. So A has the highest molarity, highest number of particle, higher number of iron. So that's why the freezing point will further decrease for a larger extent. So that's why we have lowest freezing point. All right. So for this solution, the solution is correct. I mean the answers is correct, and no problem with it. Okay, so let's move on to another one. Alright, so I will also take a new section again. Okay, so another question will be, what is the lead-ionic equation for the reaction between iron chloride with sodium hydroxide? Expect your answers as a chemical reaction including phase. Okay. What is the lead-ionic equation for part 2, magnesium sulfate and barium nitrate? Express your answer as a chemical reaction including phase. Okay, so from here we are going to look at double displacement reaction. Okay, so for this case, I believe the question just missing some of the important information because we don't know the state of iron chloride and also sodium hydroxide. And also same for magnesium sulfate and also barium nitrate. Okay, but I believe we all start with the solution. So let's look at the solution over here. We have iron chloride solution plus sodium hydroxide solution, and then we form iron hydroxide and also ammonium chloride. And then we can write a lead-ionic equation by just write down all the ions, and also we can we know the lead ionic equation over here. Okay, so it looks a little bit complicated, but let's go through that step by step. Okay, first of all, we have iron chloride. It's in aqueous, and then we have a sodium hydroxide, and also it's aqueous. All right, so I'm going to write it vertically because I'm running out of space. Okay, so for this reaction, we have a double displacement reaction. So we should be expecting the swap partner, and then we will have a sodium chloride. All right, so the two should be outside of that. Okay, so the next step we're going to balance it. So we have two chloride, so we have add two over here, so we have two in front of sodium hydroxide. Okay, so the chemical reaction is balanced, however, we're missing the phase. Okay, so for this case, we have double displacement reaction, and we likely have a precipitation reaction. So we're going back to our solubility table. We should be able to conclude that our sodium chloride must be aqueous, because sodium ion and chloride ion, when they form some chloride in aqueous solution, some chloride is highly soluble in water, So that's why it must be aqueous. So the other ion another compound that forms is the interaction between iron and hydroxide ion. Again, when we are going to look at our solubility table, we should be able to find that iron hydroxide is not soluble. It's, I would say, slightly soluble. So that's why we should have a solid being formed over here. Okay, so we have a completely full reaction equation over here, and we have to write the lead ionic equation. Alright, so for net ionic equation, you can do two different things. First of all, you can just write down all of the ion on the left like that, just like that. Doesn't matter. You can write everything look like that, and then you're going to remove the ion that have the. You can see on the left and the right. You can cancel it out, and then you will have the lead ionic equation. This is completely fine. There's no problem. Completely fine. But another easiest way, I would say faster way that you can do is that when you know the actual reaction, what species is actually reacting, you can just show those ions and then the final product, and this will be the net ionic equation. Okay, so from this case, we know that the sodium chloride is just aqueous solution. They are in it's still soluble. They are sodium ion and also chloride ion, so they just spectator ion. So we don't have to include that in the net ionic equation. And also, we know that it's iron 2 react with hydroxide ion to form iron 2 hydroxide. So we only have to show the ion that actually in the reaction, that actually take part in the reaction, and then we just show it, and then this will be the net ionic equation. So there, and then we will have a solid. Alright, so exactly the same on the left. Either way will be correct. It's up to you. Pick one of it. Okay, so another example will be magnesium sulfate with barium nitrate, and then it will form magnesium sulfate. We should start with an aqueous solution with barium nitrate, aqueous, and then they will going to form magnesium nitrate and also barium sulfate. Okay, again, balance the chemical reaction, and yeah, they are balanced. Okay, so we have to keep the phase to each of the products. So this should be aqueous. Again, referring to our solubility table. Nitrate salt, they are always soluble. But for sulfate salt, when they combine, or sulfate, when combined barium ion, they will form a salt. They are insoluble. Okay, so from here, yeah, we know that is just the sulfate ion we add with the barium ion to form sulfate ion. So we have barium ion. We first start with barium ion from barium nitrate with our sulfate ion, again from magnesium sulfate, and it will form barium sulfate. And this is the net ionic equation. exactly the same procedure to solve it when compared to part 1. And you can again, you can also express the whole equation in individual ion and then cancel out the spectator ion. You will still have the same net ionic equation. But personally, if I understand what the reaction actually going on, I will only show the ion that's actually reacting, and they will be. I don't have to waste a lot of time to just weigh out all of the ion and then just remove the spectator ion. Okay, so the solution is correct. No problem with it. Alright, so again, for the method, it's down to your personal preference. Because I know some people, they prefer to write out everything, just make sure they have everything before proceed to moving on. But if you understand the solution, you can also go with my way. Up to you. Okay, so next question. I'm going to again another section again. Okay, so what is the molar mass of helium gas? So this is very similar to the molar mass of our looking for molar mass for iron, the one of the previous question. So the molar mass of helium gas. So okay, first of all, helium gas. So helium. Let's look at helium. So helium is He, a gas. It's a inert gas. You can say we call it noble gas. Up to you. Which name we use, inert gas. Okay, so we are going to find the molar mass. All right. Okay, so from here, actually, I can tell you, I can see a different trap over here. Okay, the first trap is that, for example, if I ask you hydrogen gas, you put H2. Chlorine gas, you would put Cl2. Because for some of the gases, although they are formed by the element, but those atoms, they will going to form a diatomic molecule just to stabilize, to form a stable molecule before exits in a room temperature. So again, for H2, we have the two hydrogen combined together to form H2. Same for chlorine, because they can form a diatomic molecule. It will be easier. It will be easier for them. It will be much more stable, easier for them to exit. Okay, the reason is that because for their individual atom, they are reactive. Okay, but when we move on to look at helium, helium is an inert gas, noble gas. They are being called inert gas or noble gas for a reason, because they're stable. They're not going to react unless under some specific condition. So therefore, for helium gas, we're looking at a gastric helium atom. So in this, for example, we have mist of helium. So in the midst of helium, they are individual helium atom. They are not molecule. They are atom, individual atom. So for what we are looking at is that we want to know the molar mass of helium gas. We are going to look at the molar mass of helium, not individual molecule. Okay, so if you go back to your periodic table, so let me pull out mine from real quick, or your textbook. You should be able to find that the helium molar mass is equal to roughly around 4. So, and we are looking at molar mass, so the unit should be 4 gram per mole. 4 gram per mole. It should be 4 gram per mole. Okay, so it's pretty straightforward. Okay, so when we go back to our answers over here, it's 4.002602 atomic unit number. Obviously, this is not right because we are looking at molar mass. We are not looking at individual atom, the mass of individual atom. So the unit is not right, but the number is right. So the correct answer should be 4.002602. It will depend what kind of value you'll find, but the unit must be gram per mole. But we're looking at 1 mole of helium gas, and 1 mole of helium gas. In that helium gas, we only have atom, not diatomic molecule, but helium is stable. So we're looking at 1 mole of helium atom, and the mass will be 4.0 gram per mole. Okay, so from here, the solution is not correct. The proper unit should be gram per mole. All right, so again we have exactly the same explanation. Is that we're looking at 1 mole of atom, so we're looking at the unit gram per mole. And then we have some actual example to find out the molar mass, and this is I would say just a constant check question. So we're going to skip it. Okay, so the solution is not correct because they didn't have the right unit. Okay, so question 59, the next question. Methanol is going to burn in oxygen to form carbon dioxide and water. Write a balance equation for the combustion of the liquid methanol and calculate. I believe we have some typo error over here, and actually we are going to ask the delta H of the reaction, delta S of the reaction, and also delta G of the reaction at 25 degrees Celsius. And then we are looking at the combustion of methanol is spontaneous. So we switch gear to looking at thermodynamics. So we are delta G, delta H, delta S, and delta G. And from here, we are looking at 25 degrees Celsius, and we are looking at the standard state. So that's why we have a little circle over here. Okay, so let's look at the equation. So to determine the balance chemical reaction for combustion of methanol and call the value of blah blah blah, something like that. It's when the combustion is obviously this our solution is missing the chemical equation, and then also missing a lot of important information. But again, let's complete this solution. Okay, first of all, we have a combustion reaction with methanol. So we have CH3OH with liquid. Okay, so for combustion reaction, we are going to burn our organic compound in oxygen. So we are going to plus oxygen, and then we are going to have only CO2 and also H2O as our product. So this is called combustion reaction. So this is a complete combustion reaction. Okay, so this is the combustion reaction. The next step, we are going to balance the chemical reaction. So on the left, we have 1 carbon, so we only have to need 1 carbon. So we have 1 carbon from CO2, that is fine. And then on the left, we have 4 hydrogens. On the right, we have only have 2 hydrogen. So we have to put 2 in front of water to make sure we have the same number of hydrogen. So we have 4 hydrogens. On the left, we have 4 hydrogens. Okay, so on the right, we have 1, 2, 4 oxygen. On the left, we have 3 oxygen. So we have 2 from here, 2 from carbon dioxide, and then 2 from water. And then on the left, we have 1 from methanol, and then 2 from our oxygen. So we have 3, and we have 3 on the left, 4 on the right. So therefore, we need 1 more. I would say we need 1 more on the left. Okay, so we have 4 oxygen, and then we have 3 over here. And then in order to make sure we have 4, so I'm going to use a fraction to make things a little bit easier. So we will have 3 over 2 of oxygen. So at the end, we have 3 plus 1 is 4, and then I'll write it 4, and then we have a balanced chemical reaction. Okay, so for this question, obviously, another information missing is that we have to know the delta HF, standard enthalpy change of formation of individual chemical species, or maybe we have another delta H or delta S as central information being given. Okay, so from this case, because from your solution, from the solution, refer to appendix 2b. Actually, I don't have the textbook. I don't even know which kind of textbook is that. So I don't know what kind of information they're going to provide you or even provide me the solution. So from here, what I can tell you is that assume the most common way or most common situation that you have when you are looking at this question is that you're given delta HF. What is delta HF? Delta HF is the standard enthalpy change for formation or reaction. So you most of the time will be given at the back on textbook, given on your exam or midterm or some other source of information. Okay, so when you can find all the delta HF from the individual chemical species, and the delta H naught of the reaction, that what we are looking for, will be equals to the sum of the delta HF for our product minus the sum. This is called sigma, just a sum. The add or everything, the delta HF of our reactant. So and then you will have your number. Yeah, and then you have a number. And same thing happen. You can find the entropy of individual chemical species, and the delta S, of course, the standard entropy. Again, it's just the sum of the entropy of product minus the sum of the entropy of reactant. Yeah, so I believe those are the information given from the apprentice from the solution. Okay, so yeah, you can find delta H log, delta S log, but for delta G, the free energy change will be equals to the delta H log minus T delta S log over here. So I believe if we have that textbook, if we have that apprentice, we will have the value of delta HF. So we just need to apply this equation to solve for that. And then we also have the entropy or individual chemical species. We apply the equation to solve for that. And then we will have the delta S and delta H. And then for temperature, we are going to look at 25 degrees Celsius. But again, we are looking at Kelvin. So we are looking at 298 Kelvin. So when you and then you next step, you plug in everything, you will have found the delta G log. And this is the answers. I would say this is the general approach to solve this question, but again, this question is just missing a lot of important information, so I cannot even go through the calculation with you. But this is the strategy that we are going to use to solve for this question. Alright, so the solution is incomplete. I think I spelled wrong. Information amazing. Please revise the solution. Okay, so I'll give it incorrect. Okay, next question. Alright, so which statement are inconsistent with Dalton atomic theory as it was originally stated, and why? So first of all, A, all carbon atoms are identical. B, an oxygen atom combine 1.5 hydrogen atom to form a water molecule. C, two oxygen atoms combine with a carbon atom to form a carbon dioxide, and the formation of the product often involves the destruction of one or more products. Alright, so yeah, the solution is pretty long over here. So let me add a section again. Okay, so to summarize the delta atomic theory, just say that the building block of our chemical compound is an atom. Atom has a nucleus and electrons. When they are going to form different kind of compound, they cannot be destroyed. They must be there because it's the basic building block. Okay, so this is the basic idea. Okay, so if there's only, I would say that, okay, let's go through, there's some stuff over here. Okay, so let me summarize that. So again, as we know that from Dalton atomic theory, for each atom there's a building block. So for example, we have one building block, and then we mix it in another one. So we need to have they will form a compound. In this compound must contain these two building block, these two. But for individual atom, they cannot be further separated in much more smaller building block. But you can argue that it have proton, neutron. But we are looking at the whole atom, nucleus and electrons. Okay, so and then when they form a compound, both of them they are still here. But they just bind together. They bond together, but by ionic bond, covalent bond. So they are still there. So therefore, from here we only can find out that two statements that are inconsistent. The first statement will be the oxygen atom combined with 1.5 hydrogen atom. Again, for this building block is 1, it's a whole number. 2, 3, and 4. It cannot be 1.5. So therefore B is inconsistent. And then for the last statement is that the formation of a compound always involves destruction of one or more atom. Again, for a compound, it's a collective of individual building block atom bound together. So that's why for our answers, it will be B and D. They are inconsistent. For A, it will still consistent because for individual building block, if they are same element, they should be the same. They should be identical. And then when we are forming a compound, we must have a whole number of element or atom formed together. So only B and D, they are inconsistent. So yeah, the solution is correct. But it just, it take a very long paragraph to explain very simple concept. Okay, so we can keep going. Okay, so we are going to rearrange intermolecular force from intermolecular force of attraction from the stronger to the weakest. Okay, so we have ion dipole interaction. So wait a second, ion dipole. And then we have hydrogen bonding. I will just say H bond. And then we have a dipole-dipole interaction. And then we will have a dispersion force. Okay, so we are going to arrange according to their strength. Okay, first of all, for this question, I would say that we are looking at the general trend. Because sometimes, if you change the condition a little bit, this order may not be correct. But we are not going to pay attention to that specific example. We are going to look at the general trend. So the general trend shows that the ion dipole is bigger than stronger than the hydrogen bond. Hydrogen bond is stronger than the dipole-dipole interaction, and the dipole-dipole interaction is stronger than the dispersion force. Okay, first of all, we have to look at individual attraction. So what kind of attraction is it? Ion dipole attraction will be attraction force between ion and a dipole. So for example, sodium ion and water. Second, hydrogen bonding. We are looking at the attraction force between a molecule containing a hydrogen atom bond to something highly electronegative, and then this hydrogen atom going to interact with another atom or another molecule that are reaching electrons. Okay, for number 3, we have a dipole-dipole interaction. So we're looking at a two-polar molecule that arise from, they have a polar covalent bonding, and then they have an overall polar dipole moment that they have an overall permanent dipole and then interact with each other. And last but not least, the distribution force is the most weakest force, as you may know. And you can find it in any one of the molecule. It arises from the temporary dipole that due to the uneven distribution at a certain instant in the electron cloud or electron density, and then this temporary dipole is going to induce another dipole, and this induced dipole or instantaneous dipole with the induced dipole interaction will cause this attraction. Alright, so from this case, an iron dipole most of the time is stronger because we have a charge interact with a dipole. Because charge always have a stronger electrostatic interaction. So when they interact with a dipole, most of the time is stronger. Second, for hydrogen bonding, actually hydrogen bonding kind of special. If we look at the definition of dipole-dipole interaction, hydrogen bonding is still considered one of the dipole-dipole interaction, but it is so strong that it is considered as a separate thing. So for most of the time for hydrogen bonding, it's always stronger than dipole-dipole interaction. And of course, dipole-dipole interaction will be stronger than dispersion force. Because for dispersion force, it all depends on chance. So it doesn't always happen. So when it happens, the attraction is not that strong. So that's why it's always weaker. Okay, so I say the solution is correct, and I have no problem with the solution. So yeah, we also have looking at some concept check question. We are most of the time we are given a different molecule, and then we have to identify the molecule, and then try to figure out which one have a higher boiling point, lower boiling point, because they are the direct measurement of the intermolecular force. And then again, if you can identify, okay, do they have an iron dipole, hydrogen bond, dipole-dipole dispersion force, you should be able to answer that. Okay, so let's look at the last question of today. Okay, so for today we are looking at the last question of today. We are looking at we have to draw the Lewis structure of the disulfur monoxide, and then be sure to include all the Western structure that satisfy the octet rule. Okay, so first of all, we have as disulfur monoxide S2O. So we are going to put S2O. Okay, so S2O is okay. So we are going to draw out the Lewis structure, and then from the Lewis structure, we should be able to figure out the Western structure. The Western structure. So first of all, we have to find out the central atom. So S2O, which atom is at the center? Maybe oxygen, maybe sulfur. Okay, so if we have two situations over here, but let's figure out which one will be the center atom. Okay, so first of all, we are going to before we write out the Lewis structure, we have to find the valence electron. So for sulfur, it should be group number 4. So sulfur, we have 4 electrons. And for oxygen, I think I need my periodic table. Okay, so sulfur will be actually 6. Oxygen also is 6. Okay, I made a mistake over here. So 6 and also 6. The total number of electrons will be 18 electrons. Okay, so we will have two different possibilities. One, with our oxygen at the center. Second, with sulfur at the center. Okay, so we are going to rearrange our molecule. Okay, actually, but I moved a little bit too fast, so I should not be right in a triangular fashion. I should make sure. I just assume they are linear first. Sulfur, oxygen, sulfur. Okay, so we are going to put in electron to form a single bonding, and then we are going to put in the electron as a lone pair to fill everything. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 17, 18. 1, 2, 3, 4, 5, 6, 7. Okay, so this will be case 1. Oh my god. And then case 2. 1, 2, 3, 4, 5, 6, 7, 7, 8, 9, 10. Okay, so we will have something like that. All right, so of course, this would be the second step of joint Lewis structure. The second is because we only have 18 electrons, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. I will put an 8 over here. It may work. Okay, and then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Also put it here. All right, so we are going to try to fulfill octet rule. So we are going to draw a double bond over here, and also double bond over here, so we can remove the the electrons. All right, so apparently only the one on the left can fulfill the octet rule. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're 8 electron over here. We're 8 electron over here. And then for oxygen, 14 and 12. Okay, so for this question, it look kind of sorry, yeah, it should be something like that. Okay, so only the left one can be the one is that makes sense, and the reason is that apparently in order to make this molecule, if we have oxygen at the center, we only have one structure, and this structure cannot be changed in order to make both sulfur to have 8 electrons. Okay, so this is not right. However, if we have the sulfur at the center, because sulfur can expand its octet to have more than 8 electrons, and for this case, it can allow all 2 atoms to have 8 electrons at the same time. So only this Lewis structure is correct. Okay, so we already verified the one on the left is correct. So we are going to draw out the Lewis structure, the Western structure. So for the Western structure, it's just a Lewis structure, that is correct, and it can exist. And then we just cannot rule out that it's not a correct Lewis structure. To make it easier to be understand is that for this structure, you can write a several Lewis structure, and then by changing different bonding electron, lone pair electron, you can have different Lewis structure that can have all all atoms with octet will obey octet rules, but they will have a different arrangement in bond pair, lone pair electrons. So from this case, you keep moving the bond pair, lone pair electron, you should be able to find out the structure on the left, 1, 2, 3, 4, and then from there, you should be able to find out all 4 Lewis structure. So from here, the solution is correct, and that's it for today swimming. So if you have any question, you can